Welcome in this new class, my dear students. In the last class, I defined the direct product, and then we have to define the internal direct products and show that this Cartesian product of two groups, and this is form a group. And I also discussed some examples. The last examples for the last lecture is this one. We have to take this Z2 and Z5 consider a group, and you know that this clearly Z2 is the element of a clearly is equal to 0, 1, and we have a Z5 is the element of a 0, 1, 2, 3 and 4, and then you just take a product of all this Z2 cross the elements are into this form, and clearly now we have to try to find this if it is a cyclic or not. Suppose for example I take a because these both the groups are under addition, so I take a 1 comma 1, so this is equal to, this is simply is equal to 1 times is equal to 1 comma 1, and square means we have a 2 times of a 1 comma 1. This can be written as a 1 addition modulo 2 and 1 plus addition modulo 5, and then this is can be written in the form of a 2 is equal to, you have a 0 and then 2, and then if you have 3 times you take a 1 comma 1 can be written as a you have a this is equal to, we can take a for 2 times of a this, we adding one more 1 plus 1, so this is 1 sorry 0 addition modulo 2 1 and 2 addition modulo 5 1 is equal to, you have a 1 comma 3, and now 4 times you take a 1 1 is equal to, you have a 1 addition modulo 2 1 and 3 addition modulo 5 1, and that is equal to 1 plus 1 is 2, and that is equal to, you have a 0, and 3 plus 1 is equal to, you have a 4, and then you have a 5 times 1 comma 1 is equal to, we take a 0 addition modulo 2 1, and then you have a 4 addition modulo 5 1, and then this is equal to 1, and then 4 plus 1 is a 5, and 5 is again is a 0, then 6 1 comma 1. Now we have a 1 plus addition modulo 2 1, then you have a 0 plus 1, then you have a clearly again you have a getting this is equal to 0 and this is equal to 1, and then we have to some other we have to, you see we have a all the elements are here, so 0 1 we have to getting, 0 2 is we getting, and now 0 3 and all these things, so we have a 7 times of a 1 comma 1 can be written in the form of a you have a 0 plus 1 and then 1 plus 1, then you have a 1 comma 2, so 1 comma 2 is here, and then you have 8 times of a 1 comma 1, and then this is equal to, you have a similarly is equal to 1 plus 1 comma 1 plus 2, then is equal to 0 comma 3, and then 0 comma 3 is also here, and now we have a 9 times of 1 comma 1 can be written as a you have a 0 plus 1 and then you have a 3 plus 1, and then is it nothing but is equal to, you have a 1 comma 4, so 1 comma 4 is there. Now we have a last as a 10 times 1 comma 1, and then you have a 1 plus 1 and then 4 plus 1, and then you have a getting is equal to 0 comma 0, and then 0 comma 0 is also here. So just you see this, we have a 1 comma 1 is here, 0 comma 1 is here, 0 comma 4 is there, and then you have a 0 comma 3, and then we have a 1 comma 3. So this is generated by all the elements of this form. Then we can say that this Z2 by Z3 is generated by this single element 1 comma 1. So this is clearly, we have to just say that this is a generated by this. So this is show that this is a cyclic group. Okay, now we just take another consider the direct product of a Z2 to itself, Z2 cross Z2, and then we have only there is a 4 elements are here 0 0 0 1 1 0 and 1 1. Now 0 0 is the identity, and we have to just check 0 0 if you take add 0 0 is equal to 0, and now if you take a sum of a every element sum of this into itself, 0 plus 1 0 plus 1 0, this ka sum is equal to, you have again 0, this ka sum again is equal to 0. So every element in Z2 other than the identity has a order 2. So clearly order of this is equal to 2, order of this is equal to 2, order of this is equal to 2, and then we have a identity is the form. So every element of a Z2 cross Z2 other than the identity has a order 2, and since a group if order 4 and no element of a order 4 in it, so it is not cycle. So this means this clear group cannot be, this group is not a cycle because there does not exist any element whose order is equal to 4. So also this is an abelian group of order 4, it must be isomorphic to the Klein 4 group, and you know that the Klein 4 group is equal to, we have identity A, B and AB, the element of this types, and then you have A square is equal to B square is equal to identity, and AB ka whole square is also identities. So this means this is a if this is a group of order 4, then it is must be isomorphic to the Klein 4 group. Although Z2 and this and Z4 both contain the 4 element. Now it is see that they are not isomorphic since in AB is equal to 0, and but Z4 is, you have a clearly Z4 is a cyclic, and this is clearly I just show that this is Z2 cross Z2 is not cyclic, but Z4 is a cyclic group. So this clearly we can say that these two groups are not isomorphic to each other. So this by this example, now we move to the our result. We take a, let a G and H be an element of a G cross H. G and H have the finite order R and S. So this means order of a G to the power R is equal to identity, and H to the power S is equal to identity. Then the order of a GH in this has the least common multiple of R. Then we can say that order of this element of this G. So order of this G comma H is nothing but equal to LCM of a R and S, least common multiple of this. So we have to try to prove that if G is the order of R, so this means R to the power identity, and this is H to the power identity, then the order of this nothing but is equal to LCM of a these R and S there. So try to we try to prove this theorem. Suppose M be the least common multiples of R and S. So if this M is the least common multiple of a R and S, and let N is equal to the order of a G and H. And now if M is the least common multiple of a R and H, and then you can just simply say that we take a G H to the power M is equal to G ki power M H to the power M, and now G to the power M, and then you have a M is the least common multiple of R and S, and G to the power order of this means is a clearly identity, and this is also giving the identity. Similarly, we take this order of this is equal to N, so this means G to the power N H to the power N can be written in the form of a GH whole to the power N, and GH whole to the power N means you have a some identity, then identity of a E into identity of a J. So this means we can say that if N must divides M, and N should be less than equal to M. However, by the second equation, this second equation, R and S must divides N. Therefore, N is a common multiple of a R and S. Since M is the least common multiple of a R and S, so M should be less than equal to N, and consequently M must be equal to N. So we have to show that first is equal to N should be less than equal to M, and then by this we can say that M also less than equal to N. So by these two we can say that M is nothing but is equal to N. So this M, if you take order of this is equal to N, and M is the least common multiples of R and S, then we can say that this M and R N is the same. If M and N are the same, then we can say that the order of a GH is the nothing but is equal to least common multiple of a R and S order of this. We can extend this result for a finite number of groups. Then we take a G1, G2, Gn is the element of a G1 cross G2 cross to Gn. If Gi has a finite order, Ri in Gi, then the order of in this is the least common multiple of a R1, R2, Rn. This is the same thing we can prove for two group G and H, then we can extend direct product for the finite number of a group in the similar fashion, we can just say that. Okay, so now we just try to let this G 8 and 56 are the uh, that belongs to, we have some elements of this Z12 and Z56. Now we have to find the what is the order of this 8 and 56. Clearly you can just say that if we have some elements are there Z12, Z12 is nothing but you know that 0 to 11, and then you have a Z60 is the element of this Z60. We have a similarly 0 to 59. So 8 and 56 are the element of a clearly is equal to Z12 by Z60. Now we have to take a greatest common divisor of 8 and 12 and 56 and 60. The greatest common divisor of this is equal to 4, and the order of 8 in Z12 we can say that because of this Z12 12 or this is greatest common is equal to this. So this means add by is equal to 3. So order of 8 in Z12. So order of this element 8 in Z12 is nothing but is equal to 3, and similarly we can calculate the GCD of 56 and 60, and that is again you have a 4, and then the order of this 56 is 56 by 3 is equal to 15 in Z6. So order of this is equal to this. Now according to the theorem we can say that the order of this nothing but is equal to, so order of this we can say that order of 8 and 56 is nothing but is equal to LCM of the order of 8, order of 8 and order of 56, and LCM of order of 8 is equal to, you have a 3, order of 15 is 4 is equal to 15, then we can say simply is equal to 15. So the least common multiple of 3 and 15 is equal to 15, and this is the 56 has a order 15 into Z12 and Z60. So if you have to just check into this form, we can say that clearly that is giving to the identity element in this case. So this element, if you take any element of this as 8 into 56, then this is equal to power 15 is getting, this is the order of 8 to the power 15, and you have a 56 to the power 15, and you have to just take into this form, we can getting the value for this L equal to identity elements, this form. So this means we can, in this, by this theorem we can easily calculate the order of this any element of this. Let's try one more example. Number of actually different things. Determine the number of elements of order 7 in this. We have to this take a group is equal to 49 and 7, and now we have to find the number of elements of order 7. So how many elements of order 7 in this group Z49 by Z7. Okay, so first we have to just take a 7 is equal to nothing but equal to is the same as a LCM of order of A and order of a B. So this means we have to find the where this order of A B is equal to is nothing but the order of A and order of a B, and this is equal to 7. So there are three mutually exclusive cases. We have a possibility, or the three cases are there. First is order of A is equal to 7 and order of B is equal to 7. Then you take a LCM of a 7 comma 7 is equal to 7. So this means clearly there is a one possibility is there, and there are the 6 choices where this means for this for A, and then we have a is equal to, you have a 49. So this means is a 7, 14, 24, 28 and 42, and for a 6 choices for this 7. So you have a 7 is equal to 1 to 6. So this means you have a 6 choices for A and 6 choices for B. Then a total possibility of for a total is 36 choice elements are there. So this means we can say that is the possibility this. And now if we have a order of A is equal to 7 and order of a B is equal to 1. In this case you have a 6 choices for A, and for B is only 1 choice. So this means total is equal to 6 into 1 is equal to 6 choices are there. Another choice is A is equal to, we have a 1, or B is equal to 7. Then again for A is equal to, we have a 1 choice, and B is equal to, we have a 6 choices. Then again we have a 6 choices. So total number of choices, we have a 36 choices for this. If we have a order of A and B are 7, and then we have a order of A is equal to 7, B is equal to 1, then we have a 6 choices, and we order of A is equal to, we have a 1, order of a B is equal to 7, then again we have a 6 choices. So this means total number of possibilities are, this means we have a 48 there. So this means we can say that clearly in this has a 48 elements, has a order 7. So this means here is a, if you take a 7 into 1 and then 7 into this, so we have a 6 choices for this, 6 choices for 7, and then we have to clearly say that in this form, clearly we have to this form, this. So this means we have to, this are the possibility where the order of A is equal to 7 is equal to, only possibility is 7 to the power 1. If you take a 7 square, 7 plus 7 into this form like, okay. So this means there is a choices we have to calculate the, in this way, the how many number of elements of such a order is exist into a such a group of direct products groups is there. Okay, so now another we have to just take a find the number of a cyclic subgroup of order 14 in Z196 and Z49. So now we have to change this. We have to find the order, but not the order. We say that the cyclic subgroup of order 14. How many cyclic number of a cyclic subgroup of order 14 in Z196 and 149. So just we count the again order of AB for AB into the order 14, and there is a possibility order of A is equal to 14, order of a B is equal to, we have a 7 and 1, and then again you have a possibility are there, then you have to this thing. So this is the passive. But you see Z196 has a unique cyclic subgroup of order 14. That means we have a if it is Z96 is a unique cyclic group of order 14. So this means we have a number of cyclic generators of this is equal to 5 of 14, and then 5 14 is equal to, you have a 6, and then we have to just say that there's the means 6 generators. So we have a 6 choices for A, and then we have a 7 for B, a total 42 for A. And another we have to just say that similarly, if we have a possibility is this order of A is equal to 2 and order of a B is equal to 7, and if 2 divides 196, then phi of 2 is equal to, you have a 1 subgroup of order 2, and thus the element of a order of 2. So there are 6 choices for B. So overall 6 we have 6 choices for B. So 6 overall, we have 1 choice here and 6 choices here. We have a total is equal to, we have a overall 6 choices are there. So 42 choices from the case 1, and the second case we have a 6 choices. So we have again 48 elements of order 14 in this of a cyclic subgroup of Z of 196 by Z149 this in this example. Okay, so because each cyclic group has 6 elements of order 14, and no two of the cyclic group can have an element of order 14 in common, so there is means 48 by 6 by is equal to 8 cyclic subgroup of order 8. So this means we have a total 8 cyclic subgroup of order 14. Total number of order 14s are 48, but we have to choose how many is cyclic subgroup, because each cyclic subgroup has 6 elements of order 14, and no two cyclic subgroups have an element of order 14 in common. So there means we have to 48 by 6, you have a 8. So total number of a cyclic subgroup of this group has order 14 or 8. So total 8 cyclic subgroup of order 14 into Z 196 by Z49. Okay, now we consider one more example, and this we have to just take a consider the group Z2 by Z3, and then you know that the element of a Z2 by Z3 is equal to, in Z2 you have a only element of a 0, 1, and you have a Z3 is only an element of a 0, 1, 2. So we have to just say that similarly Z2, Z3 is equal to these elements are. Now is a group and now clearly this is an abelian group of order 6. You have 1, 2, 3, 4, 5, 6. So now we just take this clearly this is an abelian group of order 6, where 6 is this group related to another abelian group of order 6. That means we have to just say that namely Z6, or we can say that is this Z2 group Z3 is isomorphic to Z6, is this is happening. So now we try to check this is possible or not. Okay, let's try one more examples, and in this example we take consider the group of Z2 by Z3, and now you know that the element of a Z2 is equal to 0, 1, and element of a Z3 is equal to, you have a 0, 1, 2, and then if you write the elements of this, these are the total list of elements 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. So there are total 6 elements are there. So this is clearly is an abelian group of order 6. And now we just try to find out, is this group related to the another abelian group of order 6. For example, we can say the Z6, namely now the question is this Z2 by Z3 is isomorphic to Z6 or not. So let us try. We have to just find out this. So now consider a subgroup of a Z2 by Z3 generated by 1. Since the operation of each component addition, so we have a 1 into 1, 1, and then you have to just take all the elements of this is generated. So this clearly Z2 by Z3 is a cyclic group, and then if it is cyclic group, and then Z6 is also is a cyclic group. So this for Z2, Z3 is a isomorphic to Z6. Now just see this, I just write this result, because since the Z2 and Z3 these are the prime order, this is the prime order. If we have a can we extend this for a general case, if we have a ZP, ZQ is cyclic, then this is also isomorphic to Z of PQ in this way. So this next theorem tells us exactly when the direct product of two cyclic groups is a cyclic. So let we have a Zm and Zn is isomorphic to Zm Mn if and only if M and R relatively prime. That means we can say that if we have a M and R the two groups, and these two direct product of this is also isomorphic to Z of Mn whenever this M and R relatively prime. If and only if M and R relatively prime, then we can say that this is a Z and Z are isomorphic to in this form. So suppose M and R relatively prime, so GCD is equal to 1, and consider a cyclic subgroup generated by 1, 1 into Z of Mn. And now generated by 1, 1 means we have to just say that this means the order of this cyclic subgroup is the smallest power of this gives the identity element. So if means the smallest power of this one is giving the identity element, we take a power of 1, 1, and the order of this is coincide with the smallest positive integer k, such that 1, 1 plus 1, 1 plus 1, 1, and the k times is getting is equal to identity element is 0, 0. Now we use the notation of this addition for a group operation in Zm by Zn. So now if you see for the first component of the sum in the left hand side of 1 to be 0 with k to be the multiple of m. For the second component of the sum in the left hand side of this equation to be 0, we need k to be multiple of n. Thus k must be the multiple of both m and n, and the least common multiple of m and n is equal to so LCM of mn is equal to mn by GCD of mn. And now if GCD mn is equal to, you have a already giving is a 1, and then they are the relatively prime. So this means LCM of mn is equal to m of n, and then the smallest positive value of a k is mn, and then we can say that Zm and Z is isomorphic to Zmn. So we simply prove that. That means we have a, if we have a first two components of the sum of equation of this in the left hand side, you can just say that it's giving the k times, this is m times of a k, and then need a k to be multiples of a m, and because of m is the smallest, and then we have to in this case again for this case, and this case for also is a multiples of a n, and so k is a multiple of m, and k is a multiple of from this first case k of multiple of m, and this for second case is also k is multiple of n. This means k is a multiple of both m and n. So this means if k is a multiple of both of m and n, means this is the least common common multiple of m and n, and that is the k is nothing but is equal to LCM of a m and n. And so this can be written as a mn by GCD of this, and the GCD you know that already is giving is equal to 1. So this is equal to m. This is the smallest positive value k is m and n, and that means if m and n, then zm by n is a isomorphic to zmn. So this complete the one part of this. Now we conversely assume that suppose that we have a GCD of m of n is greater than 1. We have to prove the GCD is equal to 1, but we have to assuming that the GCD of mn is greater than 1. And then if it's greater than 1, then LCM of mn is less than mn. So let R be a denote is a LCM of this mn, and then we have to write a k direct sum of k is equal to 0 for all k belongs to the m, and L is a direct sum of m, this sum of m n n n n times we can take a L is the element of again Zn is equal to identity. Because this and this are the group operation in Zm and Zn, we have to denote it into this form because addition is there, so we have to take in place of this I write in this notation. Now if we have just take a k and l, so kl plus kl plus kl so on is equal to 0 for all k and l are the element of a Zm cross Zn. Now, so for any element of Zmn generate a cyclic subgroup at most r elements. So thus this Z cross Zn is not cyclic, and therefore it is not isomorphic to Zmn. And if it is not isomorphic to Zmn, but we have a hypothesis where we have a Zm by Zn is isomorphic to Zmn, and then this contradicts our hypothesis. And if this contradicts our hypothesis, means we have to our supposition this GCD is greater than equal to 1 is wrong. So this means only possibility is we can say that GCD of mn is equal to 1. So this prove the complete the proof of this result. We can say that if we have a Zmn, so this means we clearly say that if we have a Z3 divided Z 7, and this is clearly, and this is isomorphic to, if 3 and 7 are relatively prime, then this is nothing but is isomorphic to 21. And similarly you can take different, if you take a 7 multiplied by 11, and this is clearly isomorphic to z of 3 into 11, you have a 33, and similarly all this thing. So this means we can say that simply if we have a group is isomorphic, direct product is isomorphic to if m and n are relatively prime by this theorem, easily we can say that if m and n are relatively prime, then this trivially is isomorphic. This can be result can be also extend for the finite numbers of a so we have a n1 n2 and the positive integer, then this means we can say that a direct product of a z and I is isomorphic to z and n1, where GCD of ni and j is equal to 1. When we have a we can extend for a in place of a we have to taking is a two product of a two groups, then we have to extend in the case of a finite number of groups, and then we have a we can say that Zn1 cross Z of n2 cross and so on, we have a Z of nm, and then this can be written in the form of a we have a finite number of this we have a 1, or just you can write in the form of this, you have it Z1 Z2 Z3 Z1 Z2 similarly. And then if we have to write into this form, and we have to take a if this Ni, I, j, whenever I and j are different, and the GCD of a Ni and j is equal to 1, then all are relatively primes, then we can say that this is isomorphic to Z of n1 and up to nk, I running 1 to k. So this similarly we have to another corollary with this result. If m is equal to, we write a product of a power of a primes p1 to the power alpha 1, p to the power alpha 2, and pk to the power r, pi are distinct primes, then we can say that Zm is isomorphic to p to the power you can write this all the products in this one. So p to the power alpha 1 means we can say that if we have a Z4 cross Z2, and then this can say that Z4 can be written as 2 to the power 2, and this is equal to can be written as a, how you can take a 3 and the 3 to the power 1. Then is saying that you can m can be written as a 2 to the power 2 into 3 to the power 1 is equal to, you have a 4 into 3 is equal to, you have a 12, then this can be said that isomorphic to Z12. So this means we can write into this form. If we have a m can be written as a power of a primes, if this all are the prime of power, then Zm is this Z of this is isomorphic to Z of p alpha 1, p alpha 2, and pn, and so on is this form. So suppose is equal to 12. If 12 can be written as a prime of a power, you can 2 square into 3. So we can say that Zm is isomorphic to Z of 2 square into Z of 3, and then it's Z4 by Z3 in the same. So similarly you can write for all others possibilities are here, we just say that. So we have to write the proof is very simple. The greatest common divisor of this pi alpha pa, because they are all are distinct prime, and then if you take a GCD of this is clearly is equal to 1, and if the GCD is equal to 1, then the previous theorem extension of this theorem for this corollary where we say finite numbers of in this case positive integers we taking. So by this result and this we can simply say that, because you know that because this all are the distinct primes, if we take a GCD of all distinct primes, always they are relatively prime. So this greatest common divisor of this only 1, and in this case if for each I different from j, and then by using the previous corollary we can say that this means Zm is isomorphic to this is a proof is very trivial. In this case we have to in this form. This example we have to conclude this session with this example. For any n greater than 1, the group Zn is not cyclic. Because you can see if we had to say that suppose Z2 cross Z2 is not a cyclic like this, where n is greater than 1. Because if we take a GCD of these two is equal to 2 and this is less than n, we have to take a, we say that Zn is this means Z into 2 into 2, this is equal to Z4, and then clearly there is a 2 square, and then if you take a GCD of n is equal to n, and this is clearly less than of n square. So for any prime number p and q, group ZQ is a cyclic and isomorphic to ZQ as this is equal to this thing. So any group ZQ is a cyclic and isomorphic. We can say that this is equal to 2, and we have R3. We can say already ZP and ZQ are, and this is we already show that this is a cyclic group. I already show you Z2 and Z3 are cyclic, and also I just show that this is Z2 by Z3, and this is isomorphic to Z6 clearly. So this means we can simply prove this result in this case of this thing. Similar in the similar fashion, the direct product of two groups, one can define a direct product of any number of groups, and this means the theorem one point can be generalized to apply the direct product of any number of a group. So for example, if we take this example, if we have a Z2, Z3, Z5, then the constitution of a 2, 3, 5, that is equal to total is 30 elements, and then we have all the elements of A, B, C types. A is the element of Z2, B is the 3, and C. So one can check 1, 1, 1, 1, generate the whole group, and then 1 to Z2, Z3, Z5 is isomorphic to Z30, because these all threes are relatively prime, and then you can say that 2 and 3, 2 and 5, 3 and 5 all are relatively primes. And then if it is relatively prime, then the this result is say that P and Q are a group is a cyclic, and that is a cyclic. And then we have a clearly, if you check 1 comma 1 comma 1 is generate the whole the elements of this group, because all the group you have to if you take, for example, if you take a 2 times of a 1 comma 1 comma 1, and this can be written as a 1 plus under addition modulo 2 1, and then 1 plus addition modulo 1, and then here 1 addition modulo 5 1. In the similar fashion, you can just take a, this is a 0, 2 and 2, and similarly all other elements this is can generate into this form. And also you can say this is a Z30, and also this is isomorphic, because these all are the they are relatively prime, so we can say that this is isomorphic to 30, and this means also if you take these two groups Z6 and Z5, these are relatively prime to each other. If Z6 and Z5 relatively prime, then is also isomorphic to Z30, and Z2 and Z15 also relatively prime. Definitely this also is Z30. So we can, and so on, we can just find in apply this theorem. We can simply say that we can extend into this form. Okay, so this, suppose we have to example this. We have a Z12, Z21 is isomorphic to Z84 and to Z3, because Z2 and Z12 and Z21 clearly they are relatively prime, and this is relatively prime, then we can say that this is can be we written in the Z12, Z21 is isomorphic to Z12 into Z7 into, because 21 can be written as a Z21 is isomorphic to Z7 cross Z3, and then also we can say that, so this means this Z12 cross Z21 can be isomorphic to Z12 into Z7 and Z3, and now 7 and 3 is equal to 84. This can be written as a isomorphic to Z of 84 into Z of 3. So this means by this theorem we can easily find the groups are isomorphic when these are the isomorphic to each other this thing. So now with this example I conclude this lecture here, and in the next class we also continue the some other theorems of this direct product. So thank you very much for this today's lecture.